Okay, so hopefully everyone here has their exam back. I have the rest here, so I'm going to hang on to the stack until my 11 o'clock lecture and then hand those people theirs back, and then after that I'm going to distribute them out to the TAs. So anyone watching this who is not here today, you can get it from your TA your next recitation. Okay, so a few kind of administrative things. One is, as a reminder, my regrade policy is if you compare your exam to the key, which is posted online, and you feel that it was graded incorrectly or too many points were taken off based on what the points allotment on the key is, or like points were added up incorrectly or whatever, you can submit a regrade for up to 1 week after it's handed back. I think I'm actually going to extend the deadline for that just a little bit because for people in like the early Wednesday morning recitation, actually no. Yeah, okay, so I'll do the cutoff as like maybe noon on Wednesday next week. So that gives you guys just a little bit extra time. Okay, so that should work. All right, so the way you submit a regrade request is staple a sheet of paper onto the front saying, please regrade problem such and such. I feel I deserve more points back because blah, blah, blah. Try to keep it like, you know, detailed enough that I can figure out what you're asking, but short enough that I don't have to read a long essay about how you've been badly done by. And also, like, please make sure you do the extra sheet of paper because I'm not going to flip through your whole exam looking for tiny notes that you've written next to stuff. Just make it so I can sort of figure it out quickly by looking at it. Okay, and then just get it to me in any way, like either dropping it off before or after lecture, putting it in my mailbox, or handing it to me whenever. And then once that deadline closes, I'll go through the whole stack and then post regrades if I feel it was merited. Okay, so questions about that? Okay, so I guess some bigger picture things about the exam. So the average, I was really pleased with how well you guys did. So about 73.4, which means I give a 1.5 point curve. So the number written on your exam is your raw score, but in Canvas I posted the grade with the extra 1.5 on there. Standard deviation was pretty big. We covered a huge range from single digits up to a perfect score. If you're more towards the former end of that range, don't give up hope. You can still come back from it in a couple different ways. One is, I guess, like if what you're doing for studying is not working for you, definitely try some other stuff. Like if you just haven't been working problems, like that's definitely the best way to get a handle on the material, is just, you know, work as many problems as you can. But if you're sitting down and like realizing you have no idea how to even start, which is sometimes the case, then getting help while working through problems, either with a study group or like going to the help room or asking me if you've got questions. Any one of those things like might give you at least a nudge in the right direction that you can sort of learn how to figure out the rest on your own. Or I guess I think around this point in the semester the department posts like a tutor list. And those are people who have TA'd for us in the past in this class but are not currently TAing in this class. And I think the going rate is something like maybe $20 or $30 an hour if you just want to arrange to meet up with them one-on-one. That might give you a lot more like detailed attention than you can get from help room. So you've got options, and then as also a reminder, I still am offering the final exam grade replacement. So as long as you get zeros on at most 1 exam, 1 quiz, and 2 sapling homeworks, then if your final grade on the final exam is higher than like your overall course grade, I'll just use the final exam grade to replace it. Okay, so it's, you know, if you're not happy about your score, you can still come back from it, but you got to put in the work, and you got to figure out like how to put in the work effectively in a way that works for you, kind of. Okay, so any questions about any of that stuff? Okay, cool. Okay. All right, so I think I'm going to spend probably until about maybe 9:30, 9:35 answering a few problems off the exam. The ones that people probably had the most difficult time with. And then I'm going to see if I can wrap up the chapter 16 notes today so that we can get into chapter 17 next time. Okay, so let's see. Quick show of hands. How many people want me to go over? I'm going to go through all of these problems and like see like which ones people want to go over most. So problem number 1. Any votes for going over that? Yeah, I think you guys did pretty well. Problem number 2. Okay. Problem number 3. Okay, cool. A lot of hands for that. 4. Okay. 5. Okay, cool. 6. Yeah, 6 is pretty easy. 7. Okay, 6 and 7. And then how about 8? Yeah, that one was not too bad, actually. Okay, so, or sorry, not 6 and 7, 5 and 7. Okay, so I'll do number 5 first. Okay. Okay. So for this one, the question was, out of these two compounds, one goes through acid-catalyzed dehydration faster than the other. Which one is it and why? I guess from looking at these molecules, you should be getting some sort of like aromatic spidey sense starting to tingle. Like maybe they're not there just yet, but we know that dehydration, if you remember from like towards the end of OChem 1, dehydration involves removing a molecule of water, so like an H and an OH from adjacent carbons, and then forming an alkene between them. So if we do a dehydration on these things, we're going to get a double bond right there, which is going to give you that molecule, or that molecule. Okay, so one of these, I guess at this point we just want to go through and evaluate aromaticity on each of them. There is some argument to be made about stabilization during the intermediate, where you've got a carbocation that you can push around. But let's look at the final product first. Okay, so looking at this one, we end up with everything's cyclic, everything's planar. If we include the lone pairs, one of the lone pairs on oxygen, then we end up with every atom involved in the pi system, and that puts us at 8 electrons. So assuming it's planar and the lone pairs involved, then it would be anti-aromatic. If the lone pair on oxygen is in the p orbital. Whereas here, you get an aromatic product because it's got 6 pi electrons. Okay, so just on the basis of product stability, we would expect that this one is going to form a lot faster. Okay, so, yeah.
Wouldn't the product to the left just choose to be non-aromatic and just have an oxygen?
Yeah, so that's why I got this disclaimer here. So like, if the lone pair is in the p orbital, then yep, anti-aromatic, but we know it's not going to be. So non-aromatic. Mm-hmm. Yeah, so I think on the key I didn't go into that much detail. I just said non-aromatic product. Okay. So there is some argument to be made about like where the carbocation ends up during the molecule like shifting around. So I think a few people got way bogged down in showing all the resonance states. We can look at that too, but it turns out not to be that different between the two because all right, so acid catalyzed dehydration, we protonate the OH, it falls off, we get a carbocation. So like that. And then we can show, like, here's a unit of 3 atoms that hops around. To there. Or to here. Or to here. If we call these 1, 2, 3, 4, which is going to be the most stable. 4, yeah. We can do the same thing for the 5-membered ring. Once we drop off a water molecule, gets us to here. So I guess one thing I should add is that all 3 of these are probably going to be pretty minor. Like there's not a whole lot of energy, or not a whole lot of the molecule, not much of its character is going to be coming from the carbocation forms. Most of it's with the plus charge on the oxygen. And the same down here. This is the major form. And these 2 are both minor. So you could argue that this top one has more resonance forms and therefore like it's more stable, and it is a little bit, but it's a pretty small deal. Like in both cases you're getting the same stabilization from the oxygen. So it's kind of small potatoes compared to this huge, huge difference up here where we know like a lot of energy is wrapped up in aromatic versus non-aromatic stabilization. And so that's probably going to be the dominant factor, the difference between these 2 things. Yeah?
How do we know like how to distinguish between the 2? Like what if one intermediate had no resonance and the other had 4?
At that point it would be kind of a hard call.
I feel like without energy, I think it's difficult to do this problem.
Right. I guess really it comes down to like there's not a whole lot of difference in terms of like the, oh, and I lost a pi bond there, in terms of like the stabilization between the 2. And I think people who made like the resonance argument in the intermediate like still got some of the points. I don't remember if, sorry.
Yeah, actually, I was one of those people I didn't. So.
Okay. Okay, so I guess like if you're making exactly this argument that I am here, then maybe submit that for a regrade and I'll take a look and see like how, like, because I guess you could argue that if you're just looking at intermediate stability, you could argue it either way, but I think I don't know, I guess like we sort of emphasize like anti-aromatic versus aromatic is a lot of energy at stake versus here they end up being pretty similar in intermediate stability.
So in general, some products, should we focus more on that than the resonance?
I guess focus more on cases where you're comparing anti-aromatic versus aromatic or non-aromatic versus aromatic, as compared to like things where it's about the same energy, just there's one additional carbocation resonance form, which is going to be pretty minor. Yeah.
I thought reaction speed only had to do with the activation energy, like in the thermodynamic and kinetic products, they have very different product energies, but because of different activation energies, that's why it's about 90% of their products are aromatic and non-aromatic.
Right.
All have to do with activation energy, not the product.
Because would one of the 4 resonance structures be the kinetic products? Or?
I guess because it's 2 different molecules, like breaking it down into kinetic versus thermodynamic is not as clear cut. All right, so I hate to drag up the Hammond postulate from OK1. I guess you could argue it from that way, where it's sort of like because the final product is lower in energy, it's Yeah, I don't know if going into that level of detail is really fair, though, is the thing. Okay, so if this is you, if this is like the exact argument that you made and you got no points, go ahead and resubmit that and I'll take a look at it. Yeah. Okay, if you made an argument, because I did see flipping through that there's some intermediate looking things that are a bit dodgy in terms of arrow pushing, like, so if you submit for a regrade, please make sure it looks like pretty much like exactly like this if possible. Like it should be valid arrow pushing for the resonance form, and then I'll take a look. Okay. All right, so yeah, I guess that you could sort of argue it either way. Okay, so yeah, I'll take a look at what people wrote, and then if it looks like you should get a lot of points back on explaining this part, then maybe I should have sort of listed that as like a partial credit option on the key for the graders. Okay, so other questions on that? I think I'm going to move on to the next one. Okay. Okay, so let's do 7, the synthesis one. Okay. Okay, so I guess the very first thing to point out is that just because I draw it in a particular orientation in the starting material and a particular orientation in the product doesn't mean that you have to like this carbon is locked in place, because I saw a few people that like did a whole bunch of steps of like moving this alkene around to here by like subsequent addition and elimination things. You can just rotate the thing. You're okay. All right, so looking at this, there's actually a handful of ways that get you the right bond forming, but some of them are easier than others and shorter than others. So here's kind of the best possible way of doing it. All right, so we're looking at making something that has an alkyne that's sort of on a new carbon-carbon bond here. So you should probably be thinking like acetylide chemistry. Most people got that far. As far as what's going on over here, if you guys remembered, we covered one case, or I guess like in terms of the disconnect for carbon-carbon bond forming, we covered some cases where it's just the alkyne right next to the disconnect, which should make you think acetylide and alkyl halide. We covered some cases where there's a disconnect and there's some kind of oxygen functional group 2 away from that, which should be like something reacting with epoxide. If you've got both, we also covered an example of using an alkyne plus an epoxide. So the shortest possible route, although there are others, is maybe we can make that side from an epoxide and then be almost at our final product right after that happens. Okay, so let's give that a whirl. Turn this into an epoxide first. Saw a lot of people that did the capital M lowercase c PBA. It looks like something you would buy at McDonald's, but it should actually be this way around. Okay, so you make the epoxide, and then in terms of how you actually bring the acetylide in, because we're not actually making the acetylide from our main molecule, you can just roll up with that all ready to go and deprotonated. So you can just say like, this thing I will just make in some unknown like second flask somewhere and then just pipe it into the synthesis at this point. If you want to make it yourself, you can do that too, but this is really all you needed to have. and then water workup. And I'm going to start rotating this around. So like there. And then all we need to do is convert the oxygen to a carbonyl, so PCC. Okay, so that's the shortest route. Some things that are close that turn out not to work, but we haven't covered why, so I gave people full points on them, is okay, so a lot of people started out by, I guess the key step was acetylide going after an alkyl halide for them. So they do like make the halohydrin by one of a couple different methods. Either they just straight up go from the alkene, or they make the epoxide and open it with like HX, but either way they get to here, and then they PCC that. And then they bring in the acetylide in some way. Onto here, and then show it going to the product. All right, so we haven't covered it, but it turns out a lot of nucleophiles will not just go do SN2 on the alkyl halide. They're actually going to prefer to go for the base of the carbonyl, which has a bigger delta positive charge. But we haven't even started looking at that, so if you did that, good enough. It works on paper as far as we know so far. Okay, some things that did not work that you would have gotten docked points for are, so not quite, and you should know better. Is if you do the PCC after the acetylide step, what's wrong with that? Yeah, acid base. Yep, so this is a strong base. The OH is readily deprotonatable. So, whoops. So I think we did like -2 or 3 if that was the only thing you messed up, but you still got probably pretty close. Okay. So any other questions about possible answers on that one? Okay. So B was the trickier one. All right, so I'm going to draw something that a few people actually drew out explicitly that was helpful. And that is, if I rotate around here, I'm just realizing I did this on an old version of the key, so I think I scanned and posted the version before I tweaked this problem a little bit for stereochemistry. All right, so I may have to update what I posted online in the next hour, but that, if you rotate around, looks like this. And we should know from OChem 1 that Br2 on an alkene gives us anti-addition. Yeah. Okay, so All right, so I guess before we even get that far, we're going to have to add another methyl group onto the molecule anyway. So we can do that best if we get this to an alkyne first. So let's do that. We covered how to go from an alkene to an alkyne by a two-step route. So first we add Br2. And I guess you could show stereochemistry here, but it's not going to matter because this thing is going to get eliminated to an alkyne almost immediately. All right, so we were pretty flexible. I guess technically, if you've got NaNH2 to form the alkyne, if it's terminal, it'll end up with the acetylide, like the deprotonated form here. So if you want, you can just say, first off, you make the alkyne, and then it gets deprotonated at the end. And then if you were super efficient, you could just bring in like an alkyl halide at this point and have it immediately do SN2, get the methyl on there. All right, so here's where I tweaked the key a little bit, so it's going to be different from what I have online at the moment. Okay, so if we want this thing up here, we're going to have to get a transalkene. So sodium and ammonia dissolving metal reduction. So like that, and then adding Br2 gives us the right stereochemistry for the version of the exam that I eventually printed for you guys. Okay, so if you got everything right, just to use H2 and Lindlar, we only did -1 because everything else was good. But technically, if you want this particular, like both bromines dashed, then you got to come at it from the transalkene. Okay. So questions about that one? Yeah.
In that first step with the NaNH2, would you have to, is writing 3 couplets like
Actually, 1 second.
conveying a message or
Yeah, or since it's, yeah. Yeah, so you can limit it, but you don't have to. And like if people just showed this and didn't show like an acetylide or an acid workup, like generally we just kind of let it slide. So long as like maybe if the second step you did like NaNH2 again and then methyl bromide, that was good enough. So okay. Other questions about that? Okay, so a few, I guess I didn't really see any consistent kind of alternative options that people wrote. I did see a few people that got to the alkene and didn't remember you can add bromines to both carbons at once, and so they did like HBr first and then like HBr and peroxides on an alkyne or something. Problem with that is that you have no control over stereochemistry afterwards, so for that particular outcome, you're going to get like a mixture of 4 diastereomers potentially. So, okay. So other questions about that? Okay, cool. Alrighty, so I think I might just go ahead and wrap up chapter 16 for now just to get it done, and then we can start on 17 next time. Any other questions? I got the key posted, and I'll post the updated part B here, and then if you're not sure if your thing matches the key or if it's correct, like in a separate way from the key, feel free to ask me or your TAs. Okay, so the last part of this chapter, we're just wrapping up directing effects. Okay, so we spent all of last lecture looking at ortho-para versus meta-directors, but we don't really have a great way to distinguish between ortho and para because usually if a molecule allows one, it'll allow the other through resonance. So usually we get both, and then we're just going to have to separate them out however we can. You guys in lab will be covering column chromatography next week, but that's kind of our default separations method, unfortunately. However, we are sometimes able to target one over the other. by taking advantage of a couple of effects. So bulky groups are going to favor para over ortho, which is just due to sterics. So if you've got a tert butyl on the ring and you try to stick something on, like maybe another R group, then you might get some ortho, but it's going to be pretty minor, just because getting the R group to bump into the right carbon for that location is a lot more difficult. Mostly what you get is the para. Okay, getting just the ortho is trickier. Generally, you're not going to see just the ortho molecule. Okay, questions about that one? Okay, cool. Okay, so one type of case that we haven't looked at is, so far we've only looked at directing effects from one group on the ring. What if we got multiple already on there? Okay, so usually the rule is that the strongest activating group gets to decide. Or has the most influence, at least. So if we have this molecule, we've got two ortho-para-directing groups that are both activating, but OH is a better activator than CH3 is, because this one is actually activating through lone pairs, through resonance. This is only through hyperconjugation. So that one is going to say, I want groups ortho-para to me, and it's going to sort of outweigh the CH3's activating or directing effects. So the locations where you're actually going to get something added on are going to be primarily here as your major products. Okay, one other consequence is that two groups, if they're meta to each other, a third group is going to have a real hard time squeezing in between them. Just due to sterics. So if we have this molecule, the OH again is saying, I want groups ortho and para to me. So off the bat, the OH you would expect to direct groups here, here, and here. But this position is kind of blocked off due to sterics. So you're probably not going to get much addition there. It's going to be to the other two carbons. Okay, so questions about those ones? Okay, oh yeah. Because you still got two perfectly good sites on the ring to add to, and the electrophile could add here or here, so you could show the product for either one of those. So like here you would get a mixture of this thing and this thing is your product. Okay. So other questions about this case here, I guess. Okay, cool. All right, so that's pretty much all we're going to cover for directing effects. But there is one last reaction for this chapter that's totally different from everything else in the chapter, actually. So this is hydrogenation of aromatics. So we're used to seeing from like way back in OChem 1, let me draw it out explicitly. You take an aromatic ring attached to an alkene and do any sort of reaction to it, say like H2PD on C, and you are not going to touch that aromatic ring at all. That stays unchanged, and all you're touching is the alkene there. Turns out, at normal reaction temperatures and pressures, that's totally true. It's not enough to do anything to the aromatic ring. But if you just pressurize and heat the hell out of this thing, it's actually eventually going to react with the aromatic ring. So, and also it turns out if you change the catalyst up a little bit, nickel is a little bit easier for the ring to react with than palladium is. So H2 nickel, very high temperature and pressure, and you will actually eventually get that aromatic ring to hydrogenate. It takes a ton of energy to make it go, but it will eventually. Okay. All right, so I think I give like 175 degrees Celsius and 180 atmospheres, so this is not an easy reaction. And in fact, the apparatus used to do it is called a hydrogenation bomb or a PAR bomb. So yeah, it's pretty pressurized. Alrighty, so that wraps it up for chapter 16, and I'm going to be posting the 17 notes online today or tomorrow.